Welcome to week 3. In this week, we are going to discuss hashing, queues, and heaps. So today we are going to discuss about what is hashing, what are the hash tables, what are the different collision resolutions technique, what is rehashing. Then we'll discuss about queue editing, priority queues, and then heaps. So let's start. Let's start with the hashing. Whenever we store our data in any of the data structure, we always want to retrieve the data or search or insert whatever operations we want to perform. We want these operations to be performed in big O of one time. So hashing is a technique basically which we use in data structures to efficiently store and retrieve the data so that we can have a quick access. Hashing is also called mapping because we map the data on a specific index in a hash table. We generally implement hash tables using the arrays. So it allows us fast retrieval of data based on its key, or also it is also index also. So the most important thing about hashing is all the required operations, whether it is searching, insertion, or deletion of data, all of these operations can be performed in big O of one time on an average. Generally, hashing is used to map a set of distinct items and dictionaries also. It is something like you can think of that if you want to read a particular topic from the book, you are not going to go on every page of the book. Instead, you will go on the index. You will look the location of the page, a topic which you want to discuss from the index, and you directly go to that page. So basically, it makes your retrieval of data fast. For example, let's say we are having this list of numbers which we want to store in an array, which is also called as our hash table. So we are using a basic hash function here, that is x modulo 10. That is, we are taking the mod operation by 10, and whatever number we will get on that index in the array, we will put our value. For example, if the value 11 is here, so for 11, if I take 11 modulo 10, it gives me the value 1. So at index 1, we are going to map the value 11. For value 12, 12 modulo 10 is 2. So at index 2, we are going to put the value 12. The same for 13. 13 modulo 10 is 3. So at index 3, the value 13 is here. And the same goes on for value 14 and 15. So this is basically the concept how the hashing works. So if you see what are the components of hashing here, what components we have used. There are basically three components whenever we implement the hashing: key, hash function, and hash table. If we see in our previous example, this is the key, the value which we want to map in our hash table. It may be a string, it may be an integer, it may be an object, it may be any of the value which we want to store in our array. Then, so here in this example, my keys are the integer values 11, 12, 13, 14 and 15, the values which we want to put in the array. Then the next component is hash function. Hash function is, it is a function which takes your key as the input and returns an index, that at which index the value should be mapped in the array. For example, here this is our hash function. We are taking x modulo 10. So this is the hash function which is returning the index, that at which index our value should be mapped. And the third component is the hash table. Hash table is the array generally we use the array of list here. So where we are going to store the values or store the keys, where we are going to store the values, that is called as the hash table. Generally we take it as a array. If we see in this example, this is our hash table where we are storing the values. So these are basically three components of the hashing: key, the value which we want to map; hash function, the function which takes the key as the input and returns the index for the for the array at which location we are going to put the value, put the key; and the hash table where we are storing all of our values. So these are the keys which we want to map. Then by using the hash function, we get the corresponding indexes, and at these index we are going to put our values. So hash table stores key value pair. Key is the index, value is the value, original value which we want to insert in our hash table using the hash function. Basically these are of two types. One is the hash set and one is the hash map. Hash set consists of unique keys, whereas hash map consists of key value pairs. Now, let's see one more example here. Now let's say our keys are strings. For example, something like A, B, C, D, E, F, G. These are the keys which we want to map to our hash table. For the hash function, now to convert these strings to an index, we need to apply the function which is our hash function. So let's say each letter has a value, like letter A has the value 1, B has the value 2, letter C has the value 3, and so on. Our hash function will calculate sum of all the characters values and then take the modulo by table size. So AB, A equals to 1, B equals to 2. So 1 plus 2 equals to 3, and 3 modulo 7 is 3. So value AB will be mapped at index 3. CD, C equals to 3, D equals to 4. So 3 plus 4 equals to 7, and 7 mod 7 equals to 0. So this CD index string will be mapped to index 0. EFG, E equals to 5, F equals to 6, G equals to 7, which makes 18. So 18 mod 7 equals to 4. So EFG will be mapped at index 4 in our hash table. So hash function may be any function which you want to use. There are but certain properties of this hash function. So hash function basically is a function that is mapping your keys to an array index. Now, the desired properties of hash function: efficiently computable. It must be fast to compute. It should not be so long that it is taking so much time in calculating the index, right? Deterministic. It should always provide the same hash value for the same key. It should not be something like that for value AB. Sometimes it is returning index 1 and sometimes it is returning index 2. It should not be the case. Always your hash function should return the same index for the same keys. And uniform distribution. It should distribute the keys evenly across the hash table to minimize the collision. For example, if your hash table is from index 0 to 99, that is the size of hash table is 100, but your hash function is returning all the indexes up to index 25, which means it is not uniformly distributed because all the indexes are between the first 25 values. Rest of the values are empty. So a hash function should be uniformly distributed. It should uniformly distribute the keys across the whole hash table. This is a demo code that why we are for the simple hash. We are taking a string, the keys are of type string, and this is our table size. So we are calculating the addition of the ASCII values, ASCII values of each character, and then at the end we are returning the hash value modulo table size. Now you must be thinking that why we are always taking the modulo table size. In the previous example also we took mod table size. Here also we are also again taking the modulo. The modulo operation guarantees that whatever index the hash function is calculating, it is within the range of table size. For example, if your table size is 10, which means your indexes lie from 0 to 9. So, whenever you take modulo by 10, it guarantees that the result is going to be between 0 to 9. So none of the index will fall outside the range of the table size. So that is why this modulo function is necessary whenever we calculate the hash function. Again, whenever we are choosing a good hash function, it must uniformly distribute the keys to minimize the collisions. It should be fast enough to calculate the values, and it should be able to calculate the index for different type of keys. The keys may be of integer type, may be of string type, may be of date type, may be of object, user defined object, it may be anything. So it should be able to calculate the index for each type of the keys values. Now, what is the collision in hashing? Whenever multiple keys are mapped onto the same index, that is called as the collision. For example, if we use the same hash function which we developed previously, this one, I'm taking the value ABC, so its addition goes on to the 97, 98, 99. The table size is 10, so 294 modulo 10, it gives us 4. So value ABC is mapped on index 4. Now another key is CBA. For this one also, we are going to get the same value, 294 modulo 10, which is 4. So this is a collision because ABC value is already at index 4. So we cannot map another value CBA on the same index. Whenever such kind of conditions arises, whenever there is a collision, we need to apply some of the collision resolution techniques. There is one more example. If you see, we are having a key 10 and we are having a key 15. My table size is 5. So we will taking the modulo 5. If you take 10 modulo 5, it returns 0. So 10 is mapped on index 0. Now another key is 15. So 15 mod 5, which again gives us 0, but 10 is already at index 0. So we cannot put 15. So this is a collision. Now, to resolve the collision, we are having two types of techniques. One is called separate chaining and another one is open addressing. Separate chaining is also called as open hashing. Open addressing is also called as closed hashing. Open addressing again are of three types: linear probing, quadratic probing, and double hashing. Let's start with the separate chaining. So, in case of separate chaining, instead of taking an array, we take array of linked list. That means at each index, we are storing a linked list. So, for example, this is index 0, 1, 2, 3, 4, and so on. For value 10, my key is 10. For value 10, we take the modulo 5. 10 modulo 5 is 0. So 10 will be mapped on index 0. Then again the value is 15. The next key is 15. So 15 modulo 5, which is again 0. So 15 will be put as the next value in this linked list. So we do not need to overwrite the values. The collision is resolved because now we can store multiple values on the same index. So what we need to do, we need to take a linked list of an array of linked list, which we can use by creating a pointer type of um, array. So for example, we are having again an array of size 5. At index 0, there is a null pointer because there is no element. At index 1, we are having Bob, data, and then null pointer because the termination of linked list is shown by a null pointer. At index 2, we don't have any value, so null pointer. At index 3, Alice, then Charlie, and then null pointer. So collision is handled here. We are having the multiple values for the same index, so we are putting them in a linked list. Then index 4 is again null pointer. So we need to create an array of pointers to node objects. So at each location in the array, at each location, we are going to store a linked list, which will store all the values of that particular index. One more example here. Let's see, our table has 7 buckets. That means the size of the table is 7. Keys arrive in this order. So 15. So the table size is 7. So 15 modulo 7, which comes out as 1. So at index 1, the value 15 is stored. Then another value is 11. So 11 modulo 7 is 4. So at index 4, value 11 is stored. Then 27. 27 modulo 7 gives you 6. So at index 6, value 27 is stored. The next value is 8. 8 modulo 7 again gives me 1. So at index 1, we will create one more node to this linked list. And in that node, we are going to store the value 8. So collision is resolved here. So this is the one way of solving the collision. Now, another way is open addressing scheme. In open addressing scheme, instead of taking an additional data structure, instead of taking additional memory, we try to put all the values in the same array. Unlike the separate chaining. In separate chaining, we are taking the linked list at every location, at every array index. But in open addressing, what we try to do, we are not taking any additional data structure. We are just storing all the values in the same linked list. Now how it works, how the collision is resolved here, whenever a collision occurs, your algorithm will try to find out the next available position depending upon the hash function, and it insert the value at that next available slot. So for example, the probe sequence, a function that calculates the next index to check. So for example, index equals to is calculated as #1 key plus fi modulo stable size, where I is the attempt number and fi is a function defining the probe sequence. For example, insert Alice. We are getting the index 3. So at index 3, we insert the value Alice. Then again, we want to insert the Charlie. For Charlie, again, we get the index 3. So there is a collision. Now we need to resolve it. How we can do it? We are going to use the probe sequence. That is, we are going to use this another function, which will calculate the next available slot in the hash table. For example, we get the prob next available slot as 4, which is empty. So we will insert this value Charlie at the index 4. Now, open addressing, as we said, open addressing is of 3 types: linear probing, quadratic probing, and double hashing. So let's discuss what is the linear probing. In the linear probing, the probe function is simply I, which means hash key plus 0 modulo size, hash key plus 1 modulo size, hash key plus 2 modulo size, and so on until we get an empty sequence vacant slot. So let's see, our table has size 7. It's 0, 1, 2, 3, 4, 5, 6, and 6 up to index 6. Hash A, it insert at index 3. So A is index 3. Now B, we want to insert the value B, which again gives me the collision. So the value of I equals to 0. So hash key plus 0 modulo size, which is the same. So we increment the value of I. So I becomes 1. 3 plus 1 modulo table size, which gives us 4. So value B will be inserted at index 4. Now we want to insert C. So C is already occupied. Index 3 is already occupied. We check again linear probing. We put the value of I equals to 1, which gives us index 4, which is already occupied. So we take the value of I as 2, which becomes 3 plus 2 mod 7, which gives us 5. So at index 5, value C is going to be inserted. The same way, value D, let's say D gives us the index 5, which is already occupied. So we check the next available index by taking I equals to 1. So 5 plus 1 mod 7, which gives us 6. So at index 6, value will be inserted. So linear probing basically checks in the same sequence, which is the next available or which is the next vacant slot, and it will put the values in that available slot. Let's see one more example here. The table size is 7 again. We need to insert 76. So 76 mod 7 gives us 6. So at index 6, value 76 is stored. Then insert 93. So at index 93 modulo 7, which is 2. So at index 2, value 93 is stored. Then insert 40. 40 is stored at index 5. Then insert 47. 47 is stored at index 0. So for 47 we get 5. 5 is already occupied. So we will use the linear probing. We will do 5 plus 1 mod 7, which gives us 6. But 6 is already occupied. So we will go for I equals to 2. This is I equals to 1, I equals to 2. So 5 plus 2 mod 7, which gives us 0, and 0 is vacant. So 47 is stored at index 0. Then insert 10. For 10, modulo 7 is 3. 3 is vacant. So 10 is stored at index 3. Then 55. For 55, mod 7 gives us 6. 6 is already occupied. So we calculate I equals to 1, which becomes 6 plus 1 mod 7, which gives us 0. 0 is already occupied. So we take I equals to 2, which is 6 plus 2 mod 7, which gives us 1. 1 is vacant. So at index 1, value 55 is stored. So this is how the linear probing works to avoid the collision resolution. Now, the problem here with linear probing is that it forms the clusters of contiguous blocks. If a single slot has a collision, the next eye becomes more likely to have collision, so forming a cluster. And this cluster grows very fast and faster actually, which degrades the performance of hashing. Because in linear probing, if this slot is occupied, for example, the next available slot, then next available slot, and next available slot. So it forms the cluster of values by looking the next value, next available slot. So to avoid this problem, we use the quadratic probing. In case of quadratic probing, our probe function becomes fi equals to I square. Or sometimes we take C1 times I plus C2I square. Now, so the probe sequence, how the probe sequence will work? For I equals to 0, it will be hash key plus 0 mod size. For I equals to 1, it will be hash key plus 1 mod size because the square of 0 is 0, square of 1 is 1. For I equals to 2, it will be hash key plus 4 mod size, which is the 2 square. So 2 square is 4. For I equals to 3, it will become hash key plus 9 mod size because 3 square is 9 and so on. The reason for the quadratic probing is it is not finding the vacant slots linearly. It will find the vacant slot at a distance, which is the square of values. So the issue of clustering will not be there. So it will reduce the primary clusters. Now, for example, we want to insert value 4. So we insert at value 4. Sorry, insert value x at index 4. The hash function gives the index 4. It is empty. So we insert the value x at index 4. Then for value y, again we get the index 4. There is a collision. So we will check the next available slot by using the probe function, which is fi square. So it becomes 4 plus 1 mod 8, which is 5. Then next we check I equals to 2, 4 plus 4, because I equals to 2. This is for I equals to 1, this is for I equals to 2, which gives us the index 0. For I equals to 3, 4 plus 9 mod 8, which is 5, which is already checked. So there is again a problem. Now, let's see one more example. How does it works? We need to insert 18, 89, 21. So 18 is inserted at index 8, 89 is inserted at index 89, and 21 is inserted at index 1. Now, we need to insert value. Since the table size is 10, the function we are taking as by mod 10. Now, we need to insert the value 58. 58 mod 10 gives me the index 8, which is already occupied. So I equals to 0. We will calculate the next probe function. I equals to 0 is going to give us the 8, which is already occupied. We will use I equals to 1, which becomes 8 plus 1 mod 10, which gives us 9, which is already occupied. So we do I equals to 2, which becomes 8 plus 4 mod 10, which gives us 2. 2 is empty. So at index 2, we will put the value 58. Now let's say we need to insert one more value 68. 68 mod 10 gives us the index 8, which is already occupied here. So again we are going to use the probe function. For I equals to 1 gives me the 89, already occupied. I equals to 2 gives us index 2, which is already occupied. Then we check for I equals to 3. So 8 plus 9, which is 3 square. 8 plus 9 mod 10 gives us index 7. So at index 7, value 68 is stored. So just make sure that we are not performing linear probing here. We are not checking the vacant slots in a linear manner. We are checking the slots in a gap so that clustering is not there. Now, the challenges of quadratic probing. It mitigates the problem of primary cluster, but secondary clusters may be there because again you do the same hash function. Always you will get the same indexes. Always you will get the same keys. One more thing is there, even if the table is not full, the quadratic probing may not find an existing empty slot. It can cycle you through the same indices repeatedly. To guarantee that a spot is found, the table size must always be a prime number and the load factor must be kept below 0.5. Now, what is this load factor? We'll talk about this later on, but always make sure that generally to make this resolution techniques work, we use the table size always as a prime number. Now, the next type of open addressing scheme is double hashing. In case of double hashing, the probe function is I times hash 2 key. So, hash 1 key plus 0 mod size for I equals to 0. For I equals to 1, it becomes hash 1 key plus 1 times h2 key mod size. For I equals to 2, it becomes hash 1 key plus 2 times h2 key mod size. So, the offset or the index is basically determined by a second hash function applied to a key, which means that we are using the two different keys that collide at the same initial index will almost certainly have different probe sequences. Now, the requirements for hash 2 key. It must never evaluate to 0. A common choice of hash 2 is r minus key mod r, where r is a prime number smaller than table size. Let's see it with an example. Now, let's say the table size is 7, which is a prime number. Hash 1, that is my first hash function, is key mod 7. And the second hash function is 5 minus key mod r. Why we are taking a 5? Prime number less than the table size. If you see on the previous slide, we said the hash function is taken as r minus key mod r, where r is a prime number smaller than the table size. So the table size is 7, which is prime number. So we are taking smaller prime number, so which is 5. So 5 minus key mod r. Now we need to insert value 30. So my first hash function gives you, that is 30 mod 7. 30 mod 7 gives you 2. So at index 2, value is inserted 30. Let me draw the table here with the indexes. It's 0, 1, 2, 3, 4, 5, 6. Okay. 0, 1, 2, 3, 4, 5, 6. So, yes. So, now insert 16. 16 mod 2, mod 7 gives you again 2. At index 2, we put the value 30. Now 16 mod 7 again gives you 2. 2 is already occupied, that means a collision is there. So we will apply the prob function. Hash 2, hash function 2 gives you 5 minus 16 mod 5 because the key value is 16, which gives you a result of 4. So let's check for I equals to 1. So 2 plus 1 times 4, which gives you 6. So at index 6, value 16 is inserted. Now let's say another value we want to insert is 23. For 23 mod 7, again we get 2. So again a collision. So hash function 2 is calculated. 23 for value 23. So 5 minus 23 mod 5, it gives us 2. Now check for I equals to 1. So 2 times 2 plus 1 times 2. It's 2 plus 1 times 2, which gives you 4. So at index 4, value 23 is inserted. So if you see here, we were having three keys, 30, 16 and 23. For all of the three keys, we get the same index, which is 2. And by using the double hashing example, in the very first attempt, we found the different unique keys. We found the unique keys for all of these values. So there were number of operations are reduced here, and it increases the efficiency. So if we compare the probing techniques, which is linear probing, quadratic probing and double probing, the probe sequence in the linear one is calculated by hk plus I, which is the hash function for key plus I, hk plus I square for the quadratic, and in the double hashing mechanism, we use the two hash functions h1k and h2k. So it becomes h1k plus I times h2k. Linear is simple to implement, but if it suffers from the primary clustering. So we generally do not recommend it when we need to insert number of values. Quadratic probing, it reduces the primary clustering, but it may raises the issue of secondary clustering. Memory is tight, so we need to memory is tight here basically, so we need to find the table size, which is prime number. Then the double hashing scheme, it gives you the minimum clustering. Most probes are independent, but it is little complex to implement because it requires two hash functions, so it becomes slow also. Performance is critical and the hash table is large here. Now, rehashing. Rehashing is when we map all the values of our hash table to a new hash table of larger size, of greater size. What happens? Let's say my table size is 5. Index 0, 1, 2, 3, 4. The table size is 5. If we are going to insert 4 values or 5 values, there is a chance that we always get the same index values. We always get the same index value, so the number of collisions will increase and it will be difficult to map the values, and which is the target, the big O of one time of insertion, deletion and search, that will not be served. So in that case, what we do? We increase the size of our table, and from the old table, we map all the values to this new table, which is larger in size, and delete the old table. This is called as rehashing. That is, you're rehashing the existing hash table to a new hash table which is greater in size. So then the question comes, when we should perform the rehashing. It depends upon the load factor. Load factor is how much your table is filled. That is the ratio of the number of elements to the total number of buckets. That is the table size. For example, there are 3 elements currently present in the table and the size of table is 5. So 3 over 5 is your load factor. It is denoted by lambda. As much the lambda increases, the probability of collision increases, because the more the table will be filled, the more will be collisions. For separate chaining, where we uses the linked list at each index, the average time complexity shifts from big O of 1 towards big O of n as lambda grow large. But we need to keep lambda below a certain threshold to maintain the efficiency. Right? So, Why again the same? Why we are performing the rehashing? A fixed size hash table becomes inefficient as we add more and more data. So we use the rehashing when the load factor crosses a predefined threshold, for example 0.7, then we perform the rehashing. Now what are the steps of rehashing? Create a new larger array, approximately double the size, again often a prime number. For every element in the old array, recalculate its new index. Using the hash function, now make sure your table size is changed. So the index value for each key will be changed because you are going to take modulo by table size. So index will change. Then insert the element into the new array and destroy the old array. Rehashing is an additional overhead. It takes big O of n operation, but since it is not very frequent, so we can again say that the amortized cost of insertions remains big O of 1. Now, for example, let us say the table size is 4, the values are 3, which says your load factor is 0.660%, which is 3 over 5. Now, we decide to rehash when the lambda becomes greater than 0.7. So now it is 0.6, it is good. Now we need to insert a new value. So n becomes 4. So 4 over 5, my load factor 4 over 5 is 80%, which is greater than 0.7, which means we need to perform the rehashing. So we will create a new array of approximately double size. Again, it should be a prime number. So the current size is 5. So 5 times 2 is 10, but 10 is not a prime number. So next prime number is 11. So we will create a new table of size 11. Create a new array of size 11. Now, for each element in the old table of size 5, we will, we will recalculate the hash value by the table size 11 and insert into the new table. So now the elements in the new table are spread out, which will reduce the average chain length. Then, after the hashing, let's discuss the queue abstract data type. We have discussed it earlier also that it works on the principle of first in, first out. The element which is added first one is to be removed. For example, you are waiting in a queue for the bus or a ticket line. The person who is first in the line will get the bus first or get the ticket first. The operations which we use is here NQ, DQ, front is empty, is full. NQ to insert an element in the queue at the rear end. DQ to remove the first element from the queue, that is to remove the element from the front of the queue. Front or P returns the element from the front without removing it. DQ removes the element, removes and returns the element, whereas front or P just return the element without removing it. Is empty checks whether the queue is empty or not. Is full check whether the queue is full or not. Generally, we use the is full if we are having a array implementation, because in an array, the array is of fixed size. That means a limited number of elements can be inserted in the queue. Then we use the priority queue. Priority queue is again an abstract data type where each element has an associated priority with this. The element now, instead of arrival time, instead of order in the queue, the elements with the highest priority are dequeued first. You are not going to check the order of insertion. Now operations will be performed. DQ operation will be performed according to the priority. If we talk about a single normal queue, in that your arrival time is just the priority. The element which is inserted first, that will be removed first. So the order of arrival, that is the priority. But the priority may be something else also, like for example, if you're going in an hospital emergency, patients will be seen based on the severity of the condition, not by the arrival time. If we talk in terms of operating system, the processes with higher priority will get the CPU time first, the processes with the low priority will get the CPU later. So these are the priority queues. Again, if we talk about the operations and behavior which are performed by a priority queue, insert, we need to mention the priority also with the element, that what is the element with its priority, so that whenever we are going to remove the element, we can remove the element as per the priority. Get max or get min, this returns the element with the highest or lowest priority. Remove max, remove min or pop removes and returns the element with the highest or lowest priority. The element with the extreme priority, maximum or minimum, is always at the front to be accessed or removed. Yes, the priority. We are saying always highest or lowest or max or min. Why we are saying it? At some situation, higher the number, higher the priority. Like from 1 to 10, the 10 is the highest priority and 1 is the lowest priority. But at some places, lowest the number means highest the priority. That means higher the number is lower the priority, and lower the number means higher the priority. We can have both type of scenarios. So that is why we are saying highest or lowest priority, max or min. Implementing priority queue can be best done with the help of heaps. Now, what is a heap? A heap is a complete binary tree which satisfies the heap property. Now, we use the two terms here. One is the complete binary tree and one is the heap property. Okay, a complete binary tree. First of all, if I talk about the binary tree, a binary tree is a tree in which each node can have at most two child. A binary tree is a tree in which each node can have at most two child, not more than two. It can have 0, 1 or 2 child. Complete binary tree in which each level is completely filled except the last level, and nodes are inserted from the left side. For example, okay, if I say this one, and not that this one actually, okay, this is a complete binary tree actually. Now it is a complete binary tree because each level is completely filled. The at most child which can be there. Okay, if I draw it something like this, if we draw it something like this, now you see here, this level is not completely filled. This level is not completely filled and we are inserting the elements at the next level. So this is not a complete binary tree. In a complete binary tree, each level should be completely filled, only then you can move on to the next level. And the level always starts from the left side. That is, you cannot insert the element at the right end. So this is called as complete binary tree. A tree where every level 0, level 1, level 2, level 3 and so on, except possibly the last, is completely filled and all nodes are as far left as possible. Now the heap property. What do we mean by the heap property? Look, we can have two types of heaps. We can have max heap and we can have min heap. Max heap and min heap. A max heap is a heap when the value of the parent is greater than value of both of its child. When the value of parent is greater than value of any node, not only this node, for each node available in the heap. For each node, the value of that node is greater than the value of its both of child. Then it is called as max heap. And if the value of any node is less than the value of child, both child. If value of any node is less than both of its children, then it is called as min heap. So, if you're talking about the max heap, when the value of any node is greater than both of its child, so the root node will have the largest value of the tree. And in case of min heap, the root node will have the smallest value of the tree. For example, this is a min heap. If you see here, 10 is less than 15 and 30. 15 is less than 40 and 50. 30 is less than 140. So each node is less than its children. So it is min heap. Max heap, 100 is greater than 40 and 50. 40 is greater than 10 and 15. 50 is greater than, it should be 30 basically, 30 and 40. So for 50. So each node is greater than its child node. Each node is greater than its child node. So it is called as max heap. Now you can see here, in case of min heap, the root node contains the smallest value of the heap. Whereas in the max heap, the root node contains the largest value of the heap. We can represent an array. We can represent a heap by using an array. By traversing it label wise. So it is index 0, index 1, 2, index 3, index 4, index 5, index 6. So if I'm going to store this heap, this max heap in the array, it will be something like this. 100 will go on index 0, then 40, then 50, then 10, then 15, then 30, and then 40. So it will be 0, 1, 2, 3, 4, 5, 6. So by traversing your heap label wise, we can store the elements of the heap in an array. No pointers are needed. You can just directly store the tree in an array. So root always goes at index 0 for a node at index I. Now, this is the label wise traversing. Now, if you know the index, for example, this no index 3. Okay, now these are the formulas which we use to calculate the index of left child, index of right child, and index of parent. 2 times I plus 1, 2 times I plus 2, I minus 1 over 2 using integer division. Now, how does it work? Let's see at index 1. I want to find out the index of its left child. So it will be 2 times I plus 1. So the value of I is 1 here. So 2 times 1 plus 1, which gives you 2 plus 1, which is 3. So the 3 is the index of left child. Now 2 times I plus 2. So 2 plus 2, which gives you 4. So 4 is the index of right child, and index of parent node. Yes, index of parent node, which is I minus 1 division by 2. Let's say I am on index 5. I want to find out the index of its parent node. So 5 minus 1 divided by 2. 5 minus 1 is 4, 4 over 2, which gives us 2. So the 2 is the index of parent node. So these are the formulas which we use to calculate the index of left child, right child, and the parent node. Again, this is a heap. It is a min heap because it is root node is having the smallest value. So 1 is less than 3 and 6, 3 is less than 5 and 9, and 6 is less than 8. As you can see, it is the complete binary tree because each node has at most 2 child and each label is completely filled except the last label. So if you're going to store this heap in the array, so 1, 3, 6, 5, 9, 8. By label order traversing, we can store this heap in the array. Now, the basic operations of insertion and deletion in the heap. If we need to insert the element in a heap, let's say for this example, let's say I need to insert value 2. For example, I need to insert value 2. So how we are going to insert it? The first step is always insert this element as the last leftmost element on the last label leftmost element. Place the new element at the next available spot in the array to maintain the complete tree property. So how we are going to do it? I will insert the element 2 over here. Right now, okay, or let's say then if the heap property is violated, if the heap property is violated, we perform the bubble up operation. Now, what is this bubble up operation? Compare the inserted node with its parent, and if it violates the heap property, swap them. Continue swapping up until the tree is until the tree property is restored. Now, okay, if we see here in this example, my tree is satisfying the not satisfying the heap property because 6 is greater than 2. But as per the definition, every node should be smaller than, because it's a mean heap, every node should be smaller than its children. So 2 is wrongly placed here. So what we are going to do, we will compare this 2 with its parent node, 2 and 6. Since 6 is greater than 2, we will swap them. So your tree will become 1, 3, 5, 9, and here it will be 2, 8, 6. Now you can see the heap properties maintained now. 1 is less than 3 and 2, 3 is less than 5 and 9, 2 is less than 8 and 6. So the heap property is restored, so it is correct now. We perform this swapping operation till the root until the tree property is not satisfied. The complexity of insertion is big O of log n in a binary tree. Now, if we need to remove the element from the heap, okay, let's go on the same example. Let's say we want to remove an element from the heap. Always, we cannot remove any element from the between from in the heap. Always the root element is removed from the heap. Always the root element is removed from the heap. So let's say this is not here. Okay, let's see. Let me remove it. Okay, now we need to remove an element. So always root element is removed from the heap. So 1 is removed from this. Now there has to be a root in the tree. So the last element of the tree, the last element of the heap is put as the root of the heap. So your heap becomes 8, 3, 6, 5 and 9. Now, if you can see, the heap property is not maintained here because 8 is greater than 3 and 6, while we need to have the min property, so the root element should be smaller than 3 and 6. So in this case, in case of deletion, we perform the operation of bubble down. Now what is the bubble down? Compare this new root with its children. If it violates the heap property, swap it with the larger of its two children for a max heap. And for the min heap, you need to compare it, you need to swap it with the lower element. So let's do it again. Okay, so we compare 8 with 3 and 6. Since 8 is greater than 3 and 6, we compare it with 3 and 6. It is a min heap, so we will swap 8 with 3. We will swap 8 with 3. So 3 will come here and 8 will come here. Now again perform the bubble down operation. So compare 8 with 5 and 9 and swap it with the smaller element. So 5 comes here and 8 comes here. And as you can see, now it is 8 and 5. Let me erase it. So it comes 5 and it is 8. And now you can see the heap property is maintained. So this is how the deletion works. So for the insertion, you insert the element at the last vacant position, the next vacant position, and then you perform the bubble up operation. In case of deletion, we delete the root element, swap the root, then insert the last element at the root position and then perform the bubble down operation. The removing the max element or the pop operation, the complexity is again big O of log n. Now, if we have an array of elements and we need to create a heap from this. So how can we build a heap from the arbitrary array? Now, the basic method is naive method is insert each element one by one. So take one element and insert it in the tree. The other one is start from the last non-leaf node. For each node, call heapify down to ensure subtree rooted at all that means heap. Work your way to up to the root. So this is the big O of n. It takes the naive method takes big O of n log n, but this method takes big O of n. We discussed about bubble up or bubble down method. So bubble up to restore the heap property max or min upwards after a new element is inserted at the end of the heap. It is used in the insertion operation. And as we said that whenever we are going to insert a node, compare the inserted node with its parent because we are doing the bubbling up. If the elements are not in correct order, swap them and repeat the process until the heap property is restored. For the max heap, the value of any node must be greater than or equal to the values of its children. These are the steps which we need to perform. Just make sure if you're using the max heap or min heap, because for min heap, this condition will be changed. Let's say the initial heap is 30, 20, 10 and 15. The 30, 20, 10 and 15. As you can see, it is a max heap because the value of root node is greater than its children. Now you need to insert element 40. So we are going to insert 40 here, which is the next available position. Now, heap property is violated because 20 is less than 40. Whereas as per the max heap, 20 should be greater than this new element. So we are going to perform the bubble up operation. In case of bubble up operation, we will compare this 40 with its parent node. And if parent node is smaller, we will swap them. So it will become, here it will be 40 and here it will be 20. It is 40 and then 20. Now still we see The heap properties may not maintain because 30 is less than 40. Whereas for the max heap, 30, the root node, the parent node should be greater than its children. So 40 will be compared with 30. Since 30 is smaller, we will swap these values. So again, it will become, here it will come 30 and here it will come 40. And now you can see the heap property is satisfied. So your tree becomes, final heap becomes 40, 30, 10, 15, 20. 40, 30, 10, 15, 20. If the heap, it is a min heap, then your condition will be changed. Rest of the other things will remain same. In your bubble down algorithm, the same, whenever we are deleting the element, root element, which may be the max element, if it is the max heap, it will be the minimum element, the least element, if it is the min heap. So we downward compare the element. The idea is to compare the out of the place root node with its children if it is a smaller in a max heap. Then one of them swap it with the largest child. Repeat this process with the node in its new position until the heap property is restored. This is the algorithm, the same algorithm for the max heap. Okay, let's say we are having the same heap which we just took, which is 40, 30, 10, then 15 and 20. Now, if we need to delete the element, the root element which is 40, that will be removed and 20 will be at its position. So, what we are going to do, here it will be 20 and this element, this will be removed from here. So, it is 20. Now, the heap property is violated since it is a max heap. So, 20 will be compared with 30 and 10. 30 and 10, 30 is greater than 20. So we will swap these elements. So it becomes 30 here and it becomes 20. And now we can see the heap property is maintained. Because if we compare 20 with 15, 20 is greater, so nothing will happen. So your final heap becomes 30, 20, 10, 15, which is 30, 20, 10 and 15. Again, if it is a min heap, you just need to check the condition because for max heap and min heap, these conditions will be changed. Otherwise, rest of this, everything other will remain the same. So bubble up operation we use in insertion, whereas bubble down we use in the removing the element or building the heap. The direction of bubble up is upwards, whereas the direction of bubble down is downwards. We call these operations as heapify operation also. The complexity of both of these is big O of log n. Applications of heaps. These are mostly used in priority queues, uh, where the operations has to be done in terms of priority, like the operating system process scheduling, network routing algorithms, or event driven simulation. Heap sort, it is a sorting algorithm like bubble sort, selection sort, but the complexity is big O and log n. And we use it in medical triage, selection algorithms. Heaps has lots of applications. So that's all for this week. We'll meet again in the next week with the week 4. Yeah, thank you.